Hello, friends. Every computer you've ever used, your laptop, your phone, the chip inside your microwave, is built around one of two basic blueprints. One of them, the von Neumann architecture, is what powers most of the devices you interact with daily. The other, the Harvard architecture, quietly runs inside billions of smaller chips you never see. They look almost identical at first glance, but the tiny difference between them changes how fast a computer can think, how it's wired, and even what it's good at. In this video, we're going to break down exactly how these two architectures differ, why both still exist in 2026, and which one is actually sitting inside the device you're watching this on right now. Let's get into it. Before we look at what makes these two architectures different, let's quickly look at what they have in common, because honestly, that's most of it. Every computer, no matter the design, has the same four basic pieces. There's an input, your keyboard, your mouse, a sensor, something that brings information into the machine. There's a CPU, the processor, which is where the actual thinking happens. Inside the CPU, you've got the control unit, which decides what to do next, and the ALU, the arithmetic logic unit, which does the actual math and comparisons. Then there's memory, which holds the information the CPU is working with. And finally, output, your screen, your speakers, whatever shows the result to the world. Both von Neumann and Harvard agree on all of this. The CPU computes, memory stores, input comes in, output goes out. Where they disagree, and where things get interesting, is in how the CPU talks to memory. That one design choice is the entire difference between them, and it's where we're headed next.
All right, let's start with the von Neumann architecture, because this is the design almost every modern computer follows. It was proposed by mathematician John von Neumann back in 1945, and the idea was beautifully simple. Put everything, the program and the data it works on, inside the same memory. Look at the diagram. There's one big block of memory at the top. Inside it, you've got your instructions, things like add this, load that, jump here, and you've got your data, the actual numbers and values your program is crunching on. Both live together, side by side in the same physical memory. Now, here's the catch. The CPU at the bottom only has one pathway to reach that memory. We call that pathway a bus. Think of it as a single road between the processor and memory. And because there's only one road, the CPU has to make a choice every cycle. Do I go fetch the next instruction, or do I go fetch the data that instruction needs? It can't do both at the same time. It has to take turns. This is called the von Neumann bottleneck. The CPU is often sitting there, fully capable of doing more work, but waiting on that single bus to deliver the next thing. It's a little like having a brilliant chef in a kitchen with only one door. Every ingredient and every recipe has to come through the same door, one at a time, no matter how fast the chef can actually cook. So why did this design win? Because it's flexible. Since instructions and data live in the same memory, a program can be loaded, modified, or replaced just by writing different bytes into memory. That's exactly how your operating system loads apps, how a compiler turns code into a running program, and how your laptop can run a browser 1 minute and a game the next. Now let's look at the architecture that took a different approach.
Now look at this. The Harvard architecture takes one look at the von Neumann bottleneck and says, what if we just didn't share the road? Instead of a single memory holding everything, Harvard splits memory into two separate physical blocks. On the left, you've got instruction memory. This is where your program code lives, and only code. On the right, you've got data memory. This is where the values your program works on live. Two memories completely independent of each other. And here's the key part. Each memory has its own dedicated bus, its own pathway to the CPU. The instruction bus on the left, the data bus on the right. Two parallel roads. Why does that matter? Because now, in a single clock cycle, the CPU can fetch the next instruction and fetch the data that instruction needs at the exact same time. No more taking turns. No more bottleneck at the door. The chef now has two doors, one for recipes coming in, one for ingredients, and the kitchen runs at full speed. The trade-off, though, is rigidity. Because instructions and data live in physically separate memories, you can't easily treat code as data or load a new program on the fly the way von Neumann allows.
The hardware also costs more because you need duplicate memory systems and duplicate wiring. So Harvard is faster and more predictable, but less flexible. Von Neumann is flexible, but has that bottleneck. And this is where the real-world question gets interesting. Which one is actually inside your devices? Let's find out.
Let's put them side by side so the differences really click. Memory. Von Neumann uses one shared memory for both code and data. Harvard splits them into two separate memories. Buses. Von Neumann has a single shared bus, which means everything travels on the same road. Harvard has two parallel buses, so instructions and data move independently. Speed. Because of that single bus, von Neumann fetches things one at a time. Instruction, then data, then instruction again. Harvard fetches both in the same cycle, which makes it noticeably faster for tight, repetitive workloads. Flexibility. This one flips. Von Neumann is more flexible. Since code and data share memory, programs can be loaded, swapped, and even modified on the fly. Harvard is more rigid because the two memories are physically separate. You can't just treat code as data and rewrite it during execution. Cost and complexity. Von Neumann is simpler and cheaper. Fewer wires, simpler chip layout. Harvard needs duplicate memory systems and duplicate buses, which costs more silicon and more board space. And best use case. Von Neumann dominates general-purpose computing. Anywhere you need to run different programs, install apps, update software. Harvard shines in real-time and embedded systems, places where the program is fixed, predictable, and needs to run fast and on time every single time. Now, here's the twist most people don't expect. Modern processors don't actually pick one. They use a hybrid. Let me show you what that looks like. Here's what's actually happening inside the device you're using right now. Modern processors, your laptop's Intel or AMD chip, the Apple Silicon in a MacBook, the ARM chip in your phone, they don't strictly follow von Neumann or Harvard. They use a clever hybrid called the modified Harvard architecture. Look at the diagram. On the right, you've got main memory, your RAM. And just like classic von Neumann, that RAM holds both instructions and data together in one shared space, reachable through one memory bus. From the outside, the system looks von Neumann. But zoom into the CPU chip on the left, and the story changes. Right next to the CPU core, you've got two small, very fast memories called L1 caches. These are tiny pools of memory built directly into the processor itself. And here's the trick. The L1 cache is split into two. One side, the L1 instruction cache, holds recently used instructions. The other side, the L1 data cache, holds recently used data. Each one has its own dedicated pathway to the CPU core. So inside the chip, the CPU is fetching instructions and data in parallel, exactly like a Harvard machine, getting that speed advantage in the place where it matters most, where the CPU is running its fastest, tightest loops. But outside the chip, in main memory, everything still lives together like von Neumann, so you keep the flexibility to load any program, run any app, modify code at runtime. It's the best of both worlds. Harvard's speed where the chip needs to be fast, von Neumann's flexibility where the system needs to be general purpose. Pretty elegant, right? Now let's talk about where you'll actually find each of these in the real world.
So where do these architectures actually live in the real world? Pure von Neumann is mostly historical now. The original 1940s machines like EDVAC were strict von Neumann, and you'll still see the pure form in basic microcontrollers and textbooks. But almost no modern high-performance chip is pure von Neumann anymore. That bottleneck is too costly when speed matters. Pure Harvard is alive and well, just not where you'd expect. It lives inside embedded systems. The microcontrollers in your washing machine, your microwave, your car's engine controller, a lot of those are Harvard chips. Families like PIC and AVR, which power the classic Arduino boards, plus the DSPs that handle audio and radio in real time. These devices run one fixed program and need every clock cycle to count, so Harvard's parallel fetch is perfect. And then there's modified Harvard, where almost everything you actually use lives. Your laptop, your phone, the servers behind every website you visit, all of them use the hybrid we just talked about. Von Neumann RAM on the outside, Harvard-style split caches on the inside. So the next time someone asks what architecture your computer uses, the honest answer is both. Running a von Neumann program out of shared RAM, while the chip itself sneakily fetches instructions and data in parallel through Harvard-style caches, billions of times a second. A design choice made 80 years ago, still shaping every click and every tap on your screen. Let's wrap this up.
All right, let's quickly recap what we covered. Von Neumann keeps everything in one place. Instructions and data share a single memory and a single bus. It's flexible enough to run any program you throw at it, but the CPU has to take turns fetching code and data, which creates the famous bottleneck. Harvard fixes that by physically splitting code and data into two separate memories with two separate buses. The CPU can fetch both at the same time, so it's faster, but you give up flexibility, and the hardware costs more. Modified Harvard is the clever compromise that powers almost every device you actually use. Shared memory on the outside for flexibility, split caches on the inside for speed. And the bigger lesson here, the one that goes way beyond this one topic, is that computer architecture is always about trade-offs. Speed versus flexibility, cost versus performance, simplicity versus capability. There's no perfect design, just the design that fits the job. Once you start seeing computing through that lens, a lot of things, from CPUs to operating systems to entire cloud platforms, start making a lot more sense. If this helped things click, hit that subscribe button so you don't miss the next one. We've got a lot more computer science coming up on Compyra. Thanks for watching, and I'll see you in the next video.